Next chapter is solutions and colligative properties. Now, what is solution? Solution is a mixture of substances which are mixed so intimately that it cannot be distinguished with each other. So, a solution is a mixture of substances that are intermixed so intimately that they cannot be observed as separate components. These is called solution. This type of mixture is called solution. The substances which are making this solution are called components. This is component A, 1 or component 2. We'll use term solute for a component which is present in lesser extent. Or the dispersed phase or the substance which is to be dissolved is called solute. The dispersed phase or the substance which is to be dissolved is called solute and is always present in a lesser extent, whereas the dispersion medium in which that solute is dispersed is called solvent, and this solvent is always present in in excess. So after mixing solute and solvent, it will make a homogeneous mixture that is called solution. Now the next term is solubility. What is solubility? Solubility is the amount of solute dissolved in 100 grams of a solvent. The amount of solute dissolved in 100 grams of a solvent to form a saturated solution and the temperature is kept constant is called solubility. So the amount of solute dissolved in 100 grams of solvent. We are taking solvent 100 grams, and in this 100 gram solvent, the amount of solute is called its solubility, and the temperature is taken as a constant. At a given temperature it is done. Saturated solution. Our next term is saturated solution. A solution which contains as much as solute as it can hold. Then this type of solution is called saturated solution. So a saturated solution is a solution which contains as much solute as it can hold in presence of dissolving solvent at a given temperature is called a saturated solution. If the solute is in less amount, very less, as compared to its saturation, then it will be called unsaturated solution. Means this solution will require some more solutes to get saturated, and if the solute is present in excess as compared to the capacity of solvent to hold it, then it will be called a supersaturated solution. In a saturated solution, the solute and solvent proportion is in a ratio, in a fixed ratio. Means in saturated solution, a solvent can hold a particular amount of solute, so that type of solution will be called a saturated solution. And beyond this amount, if the solute amount is in excess, then this type of solution will be called supersaturated. And if this amount is very less as compared to hold by this solvent, then this type of solution will be called unsaturated solution. To keep do it saturated, in this solution we need to add some amount of solute, and for this solution we need to remove the excess amount of solute to keep it saturated solution. Now, types of solutions. There are many types of solutions are there. Depending upon the state of solute and solvent. Now we know that there are three states of matter. So on the basis of these three states of matter, these states of matter can be either solvent or solute. So we can categorize these type of solution. This will be known as binary solutions. We'll write here solute and then solvent, and here example. First we'll study gaseous solutions. If we are taking solute, a gas, or a gas is taken as a solute, and if the solvent is also a gas, we can take example of our gases. Air. In air, different types of gases are mixed. In air, the solute is gas and the solvent is also a gas, or mixture of gases. The second one is if we are taking solute as a liquid and the solvent is gas, then the example is mist or water vapors. In water vapors, as we know, water droplets are dispersed in air, so the water is our solute, which is present in lesser extent, and the dispersion medium is gas, air. So this is the example of liquid gas binary solution. The third one is solid. If we are taking solute as a solid and the solvent is again gas, can take example of smoke. In smoke, dust particles or smoke particles are dispersed in air, or we can take sublimation of a solid into gases. Sublimation of solids into gases. Solids are solute and gases are our dispersion medium or solvent. These are the example of gaseous solution. Now we'll take liquid solutions. First we'll take gas as a solute and solvent is our liquid. Example is aerated water, aerated drinks. In aerated water, the carbon dioxide or the gases are dispersed in the medium, in the water, that is our solvent. The next is the next binary solution is solid as a solute, liquid, the mixture of liquid and liquid, means solute is liquid and the solvent is also a liquid. It is the example of this is alcohol in water. Alcohol is present in lesser extent, that is our solvent, solute, and the water is in excess amount, that is our solvent. The next is the mixture of or the solution of solid into liquid. Here solute is a solid and the solvent is our liquid. Example is our sugar solution, or we can take a salt solution. Sugar and salt is our solid state and the water is our liquid state. Sugar and salt is present in lesser extent, that is our solute, and the water is in an excess amount, so it is our solvent. The next type of solutions are solid solutions. Here seventh is gas is our solute and the solvent is solid. We can take example of absorption of gases. Gases over solid. Example is hydrogen gas in palladium. Here palladium is our solid state and hydrogen is gas. So the this is our solute and this is our solvent. Solvent is in solid state and the solute is in gaseous state. Next is liquid into solid. Example is our amalgams. Amalgams is Hg in metals. As we know, the state of mercury is liquid. It is our solute. So the dispersion of mercury in metals sodium amalgam or any other kind of metals. Here the mercury is in lesser extent, and in metal is in excess extent. So this is our solute and this is our solvent, and it is the example of liquid into solid. So dispersed medium is dispersion medium is solvent and dispersed phases are liquid. The next is solid into solid. Here our solute and solvent both are solids. The example of alloys or the best example is mixing of copper in gold. When we make jewelry, we add some impurities of copper in that. So this is the example of solid solution. Here copper is in small amount, so it is our solute state, and the mercury is in larger amount, so it is our solvent. So these are the different types of binary solutions: solid solutions, gaseous solutions, and our liquid solutions. Now, the ways of expressing concentration of solutions. Of concentration. Of solutions. First we'll take concentration. What is concentration? The amount of solute present in the amount of solute dissolved in a liquid, in a solvent, is called its concentration of solution. Amount of solute dissolved in a known amount of the solvent or solution is called its concentration. So the amount of solute dissolved in a known amount of the solvent or solution is called its concentration. We'll take different expressions, different ways of expression of concentration. First is by percentage. Amount of solute per 100 parts of the solution is called its concentration in percentage. The worst is weight to weight. Weight to weight percentage is weight of solute divided by weight of solution. Into 100. This is the concentration of weight to weight percentage. If we are taking 10% of any solution, such as 10% of sodium bicarbonate, it will mean W by W will mean 10 gram of Na2CO3. Na2CO3 is dissolved in 100 gram of solution. 100 gram of solution. This 100 gram will make is made by 10 gram of Na2CO3 and 90 grams of its solution, its solvent. So 10 gram of Na2CO3 and 90 gram of solvent will make 100 gram of solution, and the percentage will be 10%, and means 10% sodium carbonate will be 10 gram of sodium carbonate and 100 gram of its solution, or we can say 10 gram of Na2CO3 plus 90 gram of its solvent. This is weight to weight percentage. If we take weight to volume percentage, then we need to take the volume of its solution and its weight of solute. So we'll write percentage weight to volume will be weight of solute and will divide by volume of solution, and for percentage we need to multiply 100. So this is the weight to volume percentage. If we say 10% of sodium carbonate, then its concentration is 10 gram of sodium carbonate into 100 ml of solution. Then this concentration will be called in weight to volume percentage. The next is volume to volume percentage. Volume to volume, then we need to write volume of solute divided by volume of solution into 100. This is the percentage volume to volume concentration. If we say 10% of alcohol, here the both the solute and solvent will be in solution will be in liquid state. So we write 10% of ethanol. It will be its volume to volume percentage will be 10 ml of alcohol into 100 ml of solution. Here this is solute and this is our solution. So the volume of solute is 10 ml and the volume of solvent will be 90 ml, and the volume of total solution will be 90 plus 10, that is our 100 ml solution. Now the next is volume to weight concentration. Volume to weight concentration, in this we'll take volume of solute and the weight of solution. If we take 10% of ethanol, we'll write 10 ml of ethanol in 100 gram of solution. It will make 10% ethanol. These were the percentage concentration. Now the next is, the second one is parts per million or parts per billion. Or parts per billion. These concentrations are present when the amount of solute is very less. Then these concentrations are expressed in terms of ppm and ppb, that is parts per million and parts per billion. So the formula for ppm is mass of solute and divided by total mass of solution. For ppm we need to multiply it by 10 to the power 6, that is million, and for ppb it will be mass of solute divided by mass of solution multiplied by 10 to the power 9 for billion. So this is the formula for concentration parts per billion. The next one is strength. Third is concentration expressed in terms of strength. Strength means the amount of solute in grams. Mass of solute in grams present in 1 liter of the solution, means volume of solution in liters is called its strength. Concentration of a solution in way of strength is mass of solute in grams present in 1 liter of solution. The unit of this is gram per liter. The next one is normality. Normality is the number of equivalents present, number of equivalents of solute present in per liter of solution, that is volume of solution. This is called normality of a solution. It is expressed in liter. So the normality of a solution is the number of equivalents, number of gram equivalents of a solute present per liter of solution is called its normality. Different formulas for normality, will write different formulas. N is equal to weight of solution, weight of solute in grams upon gram equivalent weight of solute into volume of solution in liter. The next formula is normality is equal to percentage of solute into 10 divided by gram equivalent weight of solute. Next is, if it is present in percentage, concentration is present in percentage, Then we'll write percentage weight into density into 10 divided by equivalent weight. So these are the different formulas to calculate the normality of a solution. If the volume is changed, or normality and volume is changed, the volume of a solution is changed from V1 and normality N1 to V2 and N2, then N1 V1 will be always equal to N2 V2. This is called a normality equation. So for a solution, if it is if its normality or volume is changed by V1 N1 to V2 N2 or N2 V2, then the product of its normality and volume will be always a constant. The next is when two solutions of the same solute, when two solution of the same solute are mixed, then normality of mixture will be N1 V1 plus N2 V2 divided by V1 plus V2. N1 V1 for one solution and N2 V2 for another solution. So the normality of that mixture in which the solutes are same. Here the solute 1 and here also it is 1. Then when we mix the solution N1 V1 of capacity N1 V1 and another solution which is having the same solute, the concentration is N2 and the volume is V2, then the normality of that mixture will be given by N mix is equal to N1 V1 plus N2 V2 divided by V1 and V2. Here if in another mixture if water is added, then the volume of water will become this, and it will be calculated by N1 minus N2 multiplied by V1. If in a solution if water is added, then we can calculate the volume of water by this equation. Here V2 minus V1 is the volume of water. Volume of water is V2 minus V1. If we have to calculate the normality for acid, if W gram of an acid is completely neutralized by V ml of base, then normality of will be calculated by this weight of acid upon gram equivalent weight of acid will equal to Vn divided by 1000. So by this formula we can calculate the normality of a solution when W gram of acid is neutralized by V ml of base. Similarly, we can calculate for bases, weight of base, if the weight of base is given, then we can calculate its normality by gram equivalent weight of base multiplied is equal to volume of acid into normality of acid upon 1000, or we can write Vn divided by 1000, same as acid. If the weight of acid is given, then we'll write weight of acid upon gram equivalent weight of acid, and Vn. Vn is volume of acid and volume of normality of acid divided by 1000. When VAml of acid, Va is volume of acid, Na is mixed with Vb of Nb strength, then this is our volume of acid, normality of acid, this is our volume of base and normality of base. When these are acids and bases are mixed, if VANA equals to VBNB, then this type of solution will be neutral solution, because the total amount and concentration, the product of volume and concentration of acid and base is equal. So this type of solution will be a neutral solution. If VANA is greater than VBNB, then it will be an acidic solution, because the product of normality and volume of acid is greater than the product of volume and normality of base. So this kind of solution will be acidic in nature. If the product of VBNB is greater than VANA, means the product of volume and normality of base is greater than product of volume and normality of an acid, then this type of solution will be basic in nature. So we can calculate the nature of solution. The next term for calculating the concentration is molarity. Molarity is the number of moles of a solute dissolved per volume per liter of solution is called its molarity, and it is expressed by capital M. M is equal to number of moles divided by volume. This is the formula for molarity, for calculating normal molarity of a solution, and its unit is mole per liter. Different formulas for calculating molarity is M is equal to number of moles, volume of solution in liters. First is this. The second one is, if it is given in percentage, the percentage of solute into 100 into 10 divided by molecular weight of solute. This is the another formula. If molarity and volume of solution are changed, if the molarity M1 and the volume V1 is changed to M2V2, then the product of uh, molarity and volume will be always constant. This is called molarity equation. In balanced chemical equation, if m1 moles n1 moles of reactant 1 with the n2 mole of reactant 2, then the equation will become like this: m1v1 upon n1 will be equal to m2v2 upon n2. If number of moles are given, then the in balanced chemical equation the molarity equation will become like this: m1v1 upon n1 is equal to m2v2 upon n2. If two solutions of same solute are mixed together, then the molarity of resulting solution will be equal to m1v1 plus m2v2 upon b1 plus b2. Then we can find the molarity of that mixed solution by this formula. If water is added to a solution, then we can find out the volume of water added by the equation V2 minus V1. This is the volume of water added will be equal to molarity of first solution minus molarity of second solution divided by molarity of second solution into V1. So by this formula we can find out the volume of water added to a solution. Now relation between molarity and normality. Our normality is N is given by M multiplied by molecular mass divided by equivalent mass. This is the formula relating between normality and molarity of a solution. For an acidic solution, molecular mass divided by equivalent mass is called its basicity. So N of acid will be given by molarity into basicity. By putting this, the value of this molecular mass upon equivalent mass, here we are putting basicity, so it will be like this. Similarly, as for base, for a basic solution, we can write molecular mass upon equivalent mass is equal to its acidity. Now putting the value of this molecular mass upon equivalent mass weight mass, equivalent weight of mass, then it will become like this: normality of a base and will be equal to molarity into acidity. Now the next term we'll study is molality. This is the another way of expressing the concentration of a solution is molality. Molality is the number of moles or grams of solute present in 1000 grams of solvent. So molality is number of moles or grams of solute or molecules of the solute per 1000 gram of the solvent, and its unit is moles per kilogram and is expressed by the small m. Formulas, different formulas for calculating the molality of a solution is m is equal to weight of solute number of moles of the solute into 1000 divided by weight of the solvent in grams. So this is the formula for calculating molality. The another formula is molality equals to weight of solute divided by molecular weight of solute into 1000 weight of solvent in gram. This is our number of moles into 1000 divided by weight of solvent in grams. The next formula is molality can be calculated by 10 multiplied by solubility. Solubility is our concentration of solute per molecular weight of solute. So we can calculate molality by this formula also. Now the relationship between molarity and molality. Relation between molarity and molality is molarity M will be equals to molarity divided by density minus molarity into molecular mass divided by 1000. By this formula we can calculate molality if we know the molarity of a solution, or we can write it like this: m is equal to m into d. This is our molarity. This is our molality. M into d, 1 plus small m into molecular mass divided by 1000. Or so we can calculate, if we know the concentration in terms of molality or molarity. These are the two formulas. Now the next is formality. Formality is the number of gram formula, the number of gram formula of gram formula mass of the ionic solute. Here the solution is ionic dissolved per liter of the solution is called its formality. So the formality can be calculated. If the solution is ionic, then the number of gram formula mass of the ionic solute dissolved per liter of the solution is called its formality. And the formula for calculating formality is, the formality is expressed in term of F, and F will be equal to number of gram formula mass of solute divided by volume of solution in liters. So this is the formula for calculating formality. Or we can write this formula in other form also: mass of ionic solute in grams divided by gram formula mass of solute multiplied by volume of solution in liters. By this formula we also calculate the formality. Or we can write F is equal to WB gram upon gram formula mass into volume in liters. Mole fraction. The ratio of number of moles of one component to the total number of moles present in the solution is called mole fraction. This mole fraction is independent of temperature. If we say the component A and B are present in a solution, then the molar fraction of A will be, it is denoted by X. So the molar fraction of A will be Na upon Na plus Nb. Na is the number of moles of component A, and Nb is number of moles of component B. So we can write the molar fraction of A is equal to Na, number of moles of that A component, upon total number of moles of component A and B, and the molar fraction of B will be Nb upon Na plus Nb. As we know that number of moles is equal to molecular mass upon molecular weight of that compound. For A, number of moles will be Na is equal to Ma upon Wa, and for Nb it will be equal to Mb upon Wb. So we can put these values here, and it will become as we know कि number of moles, mole fraction of compound of a solution will be always equal to 1, means the component, for component A the mole fraction is Xa, and for component B the mole fraction is B, and the total of these fraction will be always 1. Now the next term is mass fraction. Mass fraction of a component in a solution is the mass of that compound, means A or B, then mass of a component, and it will be divided by the mass of another component. It will be the mass fraction of A, and the mass fraction of B will be Mb upon Ma plus Mb. The temperature has no effect on weight, but it has significant weight on volume, so it has significant effect. So the molality, mole fraction, and mass fraction have prefer to molarity, normality, and formality. Because the former involves the weight of the solute and solvent, and later involves the volume. So these will be preferred, as these has no significant effect of temperature, but molarity, normality and formality, which is involves the weight of the solute and solvent, no, and this is preferred by volume. So molarity, mole fraction and mass fraction, which is preferred to as compared to molarity, normality and formality, because these involves the weight of the solute and solvent, and these molarity, normality and formality has the value of volume. These does not do not include the weight of solute and solvent. So these are preferred and these are not preferred, as these has no effect of temperature, and these ways of concentration have the effect of temperature. So these are preferred, and these are not preferred. Now next is Dremel unit. One Dremel unit represents the 1 mole of solute present in 1 liter of solution at 0 degree centigrade. So Dremel unit is equal to 1 mole of solute present in 1 liter of solution at 0 degree centigrade. Now the solubility. What is solubility? Solubility is the amount of solute present in solvent which is completely dissolved. The amount of solute that is completely dissolved in solvent is called solubility. Effect of temperature on solubility. Effect of temperature on solubility. Solubility is affected by the change of temperature. Generally, solubility of solid solute in liquid solvent increases by the increase of temperature. As we increase the temperature, the solubility will also increase. This is applied for the solid solute in liquid solvent. If if we are taking example, solubility changes slightly. With temperature. Examples are potassium chloride, sodium bromide, etc. For compounds like potassium nitrate, potassium bromide, solubility increases the solubility is, appreciably increases with the increase in temperature. uh, Sodium sulfate, like compounds, the solubility decreases with increase in temperature. So uh, for sodium sulfate, the solubility decreases with increase in temperature. Potassium nitrate and potassium bromide, the solubility increases with increase in temperature. And for potassium chloride and sodium bromide, the solubility changes very slightly with increase in temperature. Effect of pressure. As we know that solids are incompressible, so there will be no effect of pressure on the solvents. Solubility of gases in liquids. As we know, gases are highly compressible, so there will be effect of external pressure. The next is effect of change of temperature on solubility of gases. Solubility of gases in liquids. In liquids, and the solubility is decreases with increase in temperature. Solubility decreases with increase in temperature. And example is, as we see in water, in summers the temperature of water is increases, so the solubility of oxygen in water decreases, so the marine life is disturbed with this phenomena. As we see that the fishes go down in summers, as there is lack of oxygen in upper layer. Here the solubility of oxygen is decreases, and it will be higher in this layer, so the marine life goes downside. The next is effect of change of pressure on change of pressure on solubility of gases. There's a law for this phenomena. According to Henry's law, the solubility of gases in a liquid at constant temperature is directly proportional to the pressure. According to the Henry's law, the solubility of a gas in a liquid at constant temperature, it is directly proportional to the pressure of the gas above the solution. So we can write S directly proportional, S is solubility, S is directly proportional to P. So we can write it S is equal to Kp. Here K is proportionality constant or Henry's constant. If P is 1, that is 1 atmospheric pressure, then S will become 2K. The unit for solubility is mole per liter. Now the effect of addition of soluble salts. By adding soluble salts, the solubility is depressed, suppressed. Solubility is suppressed. So these were the effects of different change of different pressure, temperature, and salts. Now, our next topic is colligative properties. Certain properties of dilute solution containing non-volatile solute do not depend upon the nature of the solute. Certain properties of non-volatile solute do not depend on the nature of solute, but these are depend upon the concentration of these solutes, concentration that is the number of particles of solute. Means if the number of particles of solute is more, then its colligative properties will be more or less. So these properties which depend upon the depend upon the concentration of these solutes are called colligative properties, and these colligative properties are independent of the nature of these non-volatile solutes. These properties are also called democratic properties. We'll study first. There are 4 types of colligative properties. First is lowering of vapor pressure. the pressure exerted by the vapors about the liquid surface in equilibrium with the liquid at a given temperature is called vapor pressure. So if a liquid is present here and these are the vapors, so the pressure exerted by these vapors above the liquid surface in equilibrium with the liquid at a given temperature is called vapor pressure. And this pressure is in equilibrium with this liquid pressure. So this vapor pressure is depend upon the different types of things. First is nature of liquid. If a liquid is having weak intermolecular forces, then it will be volatile, easily volatile, and then it will be having greater vapor pressure. If it will be having weak intermolecular forces, then it will tend to go in its gaseous state, and if it will go in gaseous state, then it will be having more vapor pressure. So if the vapor pressure is depend upon the nature of liquid. The second one is temperature. If we increase the temperature, then the vapor pressure will also be increased. With the high temperature, the more liquid molecules will tend to go in gas state, and if the number of gas molecules are more, then vapor pressure will also more. The third one is purity of liquids. Pure liquid has high vapor pressure as compared to their solutions. As solution. The next is Raoult's law. When a non-volatile substance substance is dissolved in a liquid, the vapor pressure of liquid in a liquid, the vapor pressure of the liquid is lower, so according to Raoult's law, at any given temperature, the vapor pressure of any component of a solution is equal to its molar fraction, that is XA if we take a component A, and multiplied by the vapor pressure of this component in pure solvent, in pure state. Vapor pressure of this in pure state. So after adding a non-volatile substance, the vapor pressure is lowered and it will be equal to the molar fraction of that component multiplied by the vapor pressure of this component in pure state. We can write if the vapor pressure of this component Pa is equal to and the molar fraction is Xa, and the vapor pressure of this component in pure state is P naught A, then we can write Pa is equal to Xa into P naught A, and P total will become Pa plus Pb, and for the component B we can write Pb is equal to Xb into P naught B. The vapor pressure of component B in its pure state is P naught, and after putting this these values, the P total will become this. So the relative lowering of vapor pressure, we can write the relative lowering or of vapor pressure of a solution containing a non-volatile solute will be equal to the mole fraction of the solute. So we can write it, the relative lowering of a vapor pressure is P naught minus P naught. This is the relative lowering, and it will be equal to the mole fraction of that solute. The solute is Xb. So this is the relative lowering of vapor pressure, and the relative lowering of vapor pressure is the ratio of lowering of vapor pressure. Lowering of vapor pressure is the difference between the pressure in its pure state and is subtracted by the vapor pressure of in solution with the ratio of the pure vapor pressure of pure in pure state. This is the relative lowering, and we can write it like this also: P naught minus P upon P naught will be equal to the, we can write the molar fraction N upon N plus N. This is the molar fraction, number of moles of B component upon total number of moles, or we can write W by M. This is the weight and molecular weight of the solute and the weight and molecular weight of solvent. So this is the Henry's law of relative lowering of vapor pressure. Now limitation. Limitation of this law. This law is applicable only for very dilute solutions. If the solution is not dilute, then this law will not apply. The next is only for solutions containing non-volatile solutes. If the solute is volatile, then this law will not apply for those solutions. The next is it is not applicable to solutes which dissociate or associate in the particular solution. If these solutes are dissociates or associates in a particular solution, then this law will not apply to those solutions. Relation between Dalton's law and Raoult's law. The composition of the vapors in equilibrium with the solution can be calculated by the Dalton's law. The composition of vapors in equilibrium with the solution can be calculated by Dalton's law. Dalton's law of partial pressure. According to this law, if we take YA and YB, the molar fraction of component A and B, and we say if P is the total pressure, then we can write PA will be equals to YA plus multiplied by P. This is the molar fraction, this is the total pressure. So the partial pressure of component A will be this, and the partial pressure of B will be YB into P. And according to Henry's law, the partial pressure of A is XA into P naught A, the pressure in its pure state. This is our equation third. And for component B, the partial pressure will be equal to XB into P naught B. On equating the equation 1 and 3, it will become YAP equals to XA P naught A, and YBP will equals to XB and P naught B, or we can write YA will be equals to XA and P naught A upon P, or we can write it YA will be equals to PA upon P. So this equation will become like this, and for B component we can write YB is equal to PB upon this total pressure. So this is the relation between Raoult's law and Dalton's law. Now the difference between ideal gases and non-ideal gases. And here non-ideal gases, solutions. And for non-ideal solutions with positive deviation and with negative deviation from ideal solutions. First is ideal solution. For ideal solutions, they obey the Raoult's law. At every range of concentration, while non-ideal solutions with positive deviation and negative deviation will not obey the Raoult's law. Same. The next is the enthalpy of mixing of solutions is 0, means no absorption or evolve of heat on mixing, while in positive solutions having positive deviation will be endothermic process, means heat will be absorbed, or we can see the cooling effect after mixing. So del H of mixing of heat of mixing will be greater than 0. For negative deviation, for the solutions having negative deviation, this process will be exothermic, and the heat will be evolved, and del H of mixing will be less than 0. The next one is volume of change in volume after mixing is 0, while for non-ideal solutions having positive deviation, the change in volume after mixing is greater than 0, means volume is increased after dissolution. While for negative deviations, the volume of change in volume after mixing is less than 0, means the volume is decreased after dissolution. The next is pressure. Total pressure of all the components will be equal to the total pressure, or we can write it P naught A XA plus P naught B XB and so on will be equals, or as we know that PA is equals to here. Okay, but in solutions having positive deviation from ideal gas is PA will be greater than P naught A XA, and PB means for all the components it will be greater from its in pure state, or we can write that PA plus PB or so on, it will be greater than its pure state. But in solutions having negative deviation, the pressure of the solution will be less as compared to their the product of partial pressure of pure solvent and molar fraction, or the total pressure will be less than its in its pure state. The next is for ideal solutions, the attraction force between component AA and AB and BB will be equal, as A and B components are same in size, shape and characters. So forces will be equal, force interaction, but in non-ideal solutions having positive deviation, the AB attraction or AB interaction will be less than comparison to AA or BB, because A and B components are different in size, shape and characters. Same as in solutions having negative deviation, but here it will AB attraction will be greater than as compared to AA and BB. The same thing is here, as that A and B are different in size, shape and characters. The next difference between ideal solutions and non-ideal solution is escaping tendency of A and B should be same in uh, pure liquid and in solution. But for escaping tendency of A and B is easily they escape easily means their escaping tendency is higher for vapor pressure as than the expected value. Vapor pressure is high as compared to their expected value. And for the solutions having negative deviation, the escaping tendency is low, or their vapor pressure is low than their expected value. Example for ideal solutions are dilute solutions, all the types of dilute solution. We can take example of benzene plus toluene. These solution is shows the real ideal solutions, but water and methanol and water plus ethanol solution shows the positive deviation from ideal solution, and the solution of water and HCl, or we can take chloroform and benzene solution, these type of solutions show negative deviation. This is ideal solution. This is a non-ideal solution with positive deviation, and these are the non-ideal solution with negative deviation. We can draw a graphical diagram for these solutions. Here we are taking vapor pressure, and here the mole fraction of component A is 1 and XB is 0, and this is XB is 0 and XA is 0 and XB is 1. Here it is mole fraction. X-axis is mole fraction and on y-axis it is vapor pressure. For ideal solutions, as we know, the pressure in its pure state will be a straight line, and for component B it will be also a straight line. This is for pure vapor pressure in pure state, and the total pressure will be this. So we can write P is equal to PA plus PB. So we can see the straight line for ideal solutions, but for solutions, non-ideal solutions having positive deviation, the same thing, X is equal to 1, XB is 0, and XA is equal to 0 and XB is 1. This is the mole fraction. And for these type of solutions, it will show a positive deviation. It will show a positive curve. For this is for mole fraction A, and this is for mole fraction B, and for total pressure it will become this. This is P, this is P naught A, and this is P naught B. So this is showing a positive deviation, and this is our ideal solution for the straight line. The red one is for ideal solution and the blue is for non-ideal solution having positive deviation. Or for negative deviation we can draw negative deviation. It will be a negative curve, so this is for negative deviation. So for ideal solutions it is a straight line, for positive deviation it is a curve, positive curve, and for negative deviation the solutions having negative deviation from ideal case is a curve of negative slope. Now azeotropic mixtures. what is exotropic mixture? The mixture of liquid which boil at constant temperature. Mixture of liquids which boil at constant temperature are called azeotropic mixture, and these possess the same composition in liquid as well as in vapor phase. Same composition, or we cannot isolate the components after distillation. So the tropes are constant boiling mixture because whole of the azeotropic tropes change into vapor state at constant temperature, and their components can't be separated by fractional distillation. Two types of azeotropic mixtures are there. First, minimum boiling azeotropes. For the solution with positive deviation, there is an intermediate composition for which the vapor pressure of the solution is maximum and hence the boiling point is minimum. These types of mixtures are called minimum boiling azeotropes. But the next is maximum boiling azeotropes. For these mixtures with negative deviation, the vapor pressure is minimum and boiling point is maximum. And boiling point is maximum. So these compounds are called maximum boiling azeotropes. So for the solutions with positive deviation, vapor pressure of the solution is maximum and hence the boiling point is minimum. So these are called minimum boiling azeotropes. While as in maximum boiling azeotropes, vapor pressure is minimum for those intermediates and the boiling point is maximum. So these are called maximum boiling azeotropes. The example of the maximum boiling azeotropes are water and hydrochloric acid solution, and for minimum it is water plus ethyl alcohol solution. The next is elevation in boiling point of the solvents. Next in boiling point of the solvent, or this is called as ebullioscopy. This is our second colligative property. Boiling point of a liquid is the temperature at which its vapor pressure becomes equal to the atmospheric pressure. it will become to the atmospheric pressure, and at this pressure it will start boiling. So boiling point of a liquid is the vapor pressure, is the temperature at which its vapor pressure becomes equal to the atmospheric pressure, that is 760 mm. And since the addition of a non-volatile solute will lower um, it will lower the vapor pressure. So we need to heat this compound, this solvent, this solution. Heat will be needed to raise its vapor pressure to equal this the atmospheric pressure. So it will its boiling point will be increases, and boiling point of a liquid is the temperature at which its vapor pressure becomes equal to the atmospheric pressure, and since the addition of a non-volatile solute will lower the vapor pressure of the solvent, and solution has lower vapor pressure and then the solvent, and will be needed to heat at high temperature to make its vapor pressure equals to atmospheric pressure, or we need to raise the temperature, and resulting the solution will boil at high temperature. High temperature as compared to its pure solvent. So there will be a difference in between the boiling point of this solution as compared to the boiling point of pure solvent, and this will be called as elevation in boiling point of the solvent. As we know, the sea water boils at a high temperature. Why it boils at high temperature? Because there are more solutes as compared to pure water or distilled water. So it will be boiled at high temperature. The boiling point of solvent is TB, and we can write an elevation of boiling point we can write it T minus TB, that is del TB, or we can write del T. This is for solution, and TB is for it's a boiling point of pure solvent, and this is our elevation in boiling point. This elevation in boiling point is can be determined by Lenzburzer's and Cottrell's method. And the study of elevation of boiling point of solvent is called ebullioscopy. The elevation in boiling point is directly proportional to the lowering of vapor pressure, or we can write del TB is directly proportional to, this is the lowering of vapor pressure, or we can write it in the other form, that is Kb into m. M is our molality and Kb is molar elevation constant, or we can write it in the form of 1000 into Kb into W upon m into W, that is our molecular mass and weight. Or we can write molality will be equals to 1000 into Kb into W upon W, capital W, into del TB. Here W, small w, is the weight of solute and capital W is the weight of solvent. Our next formula for calculating is Kb will be equals to 0.002 T naught 0 square and LV. This is LV is the latent heat of evaporation, and T naught is normal boiling point. Boiling point of pure solvent. So these are the formula for calculating the lowering of for the elevation of boiling point. Or we can draw a graphical diagram for elevation and boiling point. Here is the pressure and here temperature scale. This is our atmospheric pressure and this is our solvent. This is for solution 1 and this is for solution 2. Solution 1 and solution 2. For this is the P0 and this is our T0, this is T1. So this is the elevation of boiling point. This is for pure solvent and this is D1 is for solution 1 and T2 is for solution 2. So there is a elevation of boiling point for solution 1 and this is for the elevation of boiling point for solution 2. Our next colligative property is depression in freezing point of the solvent. The study of depression in freezing point of the solvent is called cryoscopy. First, we'll study what is freezing point. Temperature at which liquid and solid state of a substance are found in equilibrium. Is called its freezing point, or we can say at freezing point the vapor pressure of a liquid and solid state is equal. This is our liquid and this is our solid. At a freezing point, they both are found in equilibrium. So, after adding a solute, the freezing point of any solvent is get depressed, or freezing point of solution is found less as compared to pure solvent. As we know that the freezing point of seawater is very less as compared to its pure state, that is our pure water. What is the depression of freezing point of a solvent is the difference in freezing point of pure solvent and its solution. So this is the difference between the freezing point of pure solvent and its solution is called depression in freezing point of a solvent, and we can measure it by T of solvent minus T of solution. This is the freezing point of solution, this is the freezing point of pure solvent, and the difference of these freezing points will be equal to depression in freezing point of a solvent, that is del T F, or we can write del T. Now we can take one example. Sodium chloride and calcium chloride, anhydrous sodium chloride and calcium chloride are used in clearing the snow, as these compounds lowers the freezing point of snow of snow, and these compounds are used to clear snow on road. Freezing point is depression in freezing point is determined by many methods. The one is Bachman Bachman's method. The another one is Ras Camphor method. By two these methods we can determine the depression in freezing point. Now the factors, how we can calculate the depression in freezing point. Depression in freezing point is directly proportional to the lowering of vapor pressure. This is our depression in freezing point, and this is it is directly proportional to the depression in lowering of vapor pressure, or we can write it depression in freezing point is equal to Kf into m. M is our molar depression, molality of solution, and Kf is molar depression constant, or we can say cryoscopic constant, or we can calculate the depression in freezing point by this formula also, 1000 into Kf multiplied by W upon M into W, or molality can be calculated by this 1000 into Kf into W upon del Tf into W. So these are the formula to calculate the depression in freezing point. Here M is our molality of solution, and W this W is the weight of solute and solvent and solution. Or we can calculate, we have one more formula for calculation, that is Kf is equal to R T0 square upon LF into 1000, or we can write 0.002 T0 square upon LF. LF is latent heat of fusion. The LF is latent heat of fusion per gram of solvent, or T0 is the normal freezing point of solvent. We can draw a graph for the depression and freezing point. Here it is our vapor pressure on y-axis, and here it is the temperature, that is depression and freezing point. here it is this is our solid state, and here it is liquid state. This is for solvent, pure solvent, for solution 1, and this is for solution 2. So the freezing point for the solvent, pure solvent, is this is our T0, this is T1, and here it is T2, and this is our vapor pressure for pure solvent, and here it is vapor pressure for solution 1 and the vapor pressure for solution 2. So this is the difference between solvent and the solution 1, the depression and freezing point of this solution for solution 1, and for solution 2 it is T0 minus T2, that is the depression and freezing point for solution 2. The next colligative property is osmosis, or first we study what is osmosis. Osmosis and osmotic pressure of the solution. The flow of solvent from pure solvent to from pure solvent or from lower concentration from the solution of lower concentration to higher concentration is called osmosis, and this osmosis is occurred through a semi-permeable membrane is called osmosis. If this is a semi-permeable membrane, here is the solution 1 and here is the solution 2. And this solution is having lower concentration, and this has high concentration. So what is osmosis? Osmosis process is occurred only by the molecule of solvent. Solvent molecules only travel. Not this solute. So the solvent molecule will move from lower concentration to higher concentration. So the moving of solvent molecule is through this, and this process will be called osmosis. Now, types of osmosis. Osmosis are of 3 types. First, exoosmosis. the inward flow, the outward flow of water from a cell containing an aqueous solution through our semi-permeable membrane is called exoosmosis. When example is when we put an egg without shell, and when we keep it in aqueous solution or in concentrated solution of sodium chloride, not with then this egg will shrink. So this is our sodium chloride solution, and when we put the egg inside, the water from egg or the fluid from egg, the water will come out in this solution and the egg will get shrink. This is called exoosmosis because the water from any body is coming out in the aqueous solution. So this is called exoosmosis. The next one is endoosmosis. As the name is suggesting, water is going inside, or the inward flow of water into the cell is called endoosmosis. If we put egg in water, this is our egg. After putting in water, it will get swollen up. Why it will swell up? Because of endoosmosis, the water of this container will get into the egg and the egg will swell up. This process is called endoosmosis. The third term is reverse osmosis. If we put the pressure, or we put higher pressure as compared to our osmotic pressure, then the solvent will flow from the solution into the pure solvent, is applied on solution. Then the solvent will flow from the solution into the pure solvent. It is just opposite to the osmosis, the pure solvent through a semi-permeable membrane. This process is also happening through the semi-permeable membrane. is uh, is called reverse osmosis. The flow of solvent is in reverse direction to the observed in the usual osmosis, so this is called reverse osmosis. This is our pure solvent, and this is our semi-permeable membrane, and here it is solution. So the solvent will flow from the solution into the pure solvent through semi-permeable membrane. It will happen this exosmosis, reverse osmosis. In osmosis, it is going from pure solvent to solution, but in reverse osmosis, it is going from a solution to the pure solvent, and this process will happen only in presence of high pressure. As we are applying pressure to reverse this process is called reverse osmosis. The difference between osmosis and diffusion, as we have studied what is the diffusion. Diffusion is the flow of any molecule from higher concentration to the lower concentration, and in osmosis the same process is going on, but there's some difference. In osmosis, molecules move from lower concentration to higher concentration, but in diffusion the molecules move from higher concentration to the lower concentration. This process happens through the semi-permeable membrane. But there is no role or no requirement of semi-permeable membrane. It involves the movement of solvent only. Only solvent molecule movement of solvent molecule only. Here both the solvent and solute molecule move from higher concentration to the lower concentration. It is limited to the solutions only. While diffusion happens in liquid, gases, and as well as in solutions. For osmosis, it can be stopped or it can be reversed by applying of forces, or pressure. But in diffusion, it is not done. So these were the differences between osmosis and diffusion. The next, the term we are talking, hearing again and again is semi-permeable membrane. What is a semi-permeable membrane? Semi-permeable membrane is one which allows only solvent molecule, not and no solute molecules are allowed to pass through. Two types of semi-permeable membranes are there. First is natural, which we can found in living beings as a cell wall in plants or gallbladder and animals. These are the natural semi-permeable membrane, and these semi-permeable membranes are not perfect and can't afford the higher pressure. If we put the pressure high, then it will break down or it will tear off. The next is artificial semi-permeable membrane. Examples are parchment paper, or cellophane papers. These are synthetically prepared and can afford high pressure. So we can use these for these semi-permeable membranes in presence of high pressure. Now, what is osmotic pressure? Osmotic pressure is denoted by the symbol pi. The excess pressure which must be applied to a solution in order to prevent the flow of solvent. Into the solution is called osmotic pressure. So this pressure is the force which is stopping that osmosis process. So the excess pressure which must be applied to a solution in order to prevent the flow of solvent into the solution through the semi-permeable membrane is called osmotic pressure. Or we can say this is the opposing pressure. Measurement of osmotic pressure is done by these are the methods: Pfeffer's method, and the second is Berkeley and Hartley's method. Berkeley and Hartley's method. Now, laws of osmotic pressure As we have studied the laws for gaseous gas laws, same as for the some laws are there for solutions. These are called laws of osmotic pressure. First is Van Hoff. According to Van Hoff, like gas molecules, solution in solutions, solute particles also uh, move randomly and exerts pressure on the wall of container. These are molecules of solute. These are moving randomly and it exerts some pressure on the sides of the container. This pressure is called osmotic pressure. So according to Van Hoff, the pressure applied by solute molecules on the sides of the container is called osmotic pressure. The second law is Van Hoff-Ball's law. According to this law, the osmotic pressure is directly proportional to the concentration uh, at uh, at constant temperature. So we can write this is the our osmotic pressure. The osmotic pressure is directly proportional to the C concentration, or we can write pi is inversely proportional to volume. This is Van Hoff-Ball's law. The third one is Van Hoff and Charles law. According to this law, the osmotic pressure is here the term is used dilute solution. So these laws are only applied in case of dilute solution. So osmotic pressure of a dilute solution is directly proportional to the absolute temperature. So osmotic pressure is directly proportional to the absolute temperature, and here the concentration is kept constant, or as we know that C is equal to N by V, so we can keep the volume also constant. The fourth law of osmotic pressure is this is the first we will give the general equation for osmotic pressure. By adding all these laws, want of Boyle's law, want of Charles law, we can get one equation. Pi v is equal to nRT, or this is the general equation for of osmotic pressure, or we can write it pi is equal to n by v upon RT. As we know, C is equal to n by v. So we can write the values here. Pi is equal to CRT, or we can write pi is equal to n by v RT will be equivalent to pi is equal to W upon capital W to pi RT upon V. Here W is the weight of solute and capital W is molecular weight of solute. So this is the want of equation or the law of osmotic pressure. Want of equation or the law of osmotic pressure. Now the next law is want of Avogadro's law. The fifth one is want of Avogadro want of equation and want of Avogadro's law. Under similar conditions of temperature and pressure, under similar condition of temperature and pressure is osmotic pressure, the equal molecule of all dilute solution contain the same number of molecules. So we can write the V is directly proportional to N, or V1 upon V2 is equal to N1 upon N2. So this is want of Avogadro's law for dilute solutions. Now if we take osmotic pressure of mixture of two solutions, what will happen? Osmotic pressure of mixture of two solutions. If we are mixing two solutions, then what will happen to the osmotic pressure? First case is if two solutions of same solutes are same but are having different osmotic pressure, then what will happen? Osmotic pressures are suppose pi 1 and pi 2. If these two solutions are mixed, then the combined osmotic pressure will be given by pi 1 V1 plus pi 2 V2 will be equals to pi R B1 plus V2. Here pi R is the resultant osmotic pressure of mixture, of mixture, and V1 and V2 are the volume of solutions, different volumes of solutions. The case 2 is if we are taking N1 and N2 moles of two different solutes present in V1 and V2 volume, then pi of mixing means the resultant osmotic pressure will be equals to pi 1 plus pi 2, or we can write N1 I1 RT upon V1 plus V2. This is the value of pi 1 plus N2 I2 RT upon V1 plus V2. This is the value of pi 2, or we can write pi is equal to N1 I1 plus N2 I2 upon V1 plus V2 and RT. So the pressure osmotic pressure of mixing or resultant osmotic pressure will be given by N1 I1 plus N2 I2 upon V1 plus V2 multiplied by R2 RT. Here I is the Van Hoff factor. Now, what is the relation between different colligative properties and osmotic pressure? Between different colligative properties and osmotic pressure. First is the relation between the lowering of vapor pressure. The pi is equal to P naught A minus P upon P naught A. This is the relative lowering of vapor pressure into dRT upon M. This is the relation between the relative lowering of vapor pressure and osmotic pressure. The second one is the elevation of boiling point. Pi is equal to del TB into dRT upon 1000 into KB. This is the relation between osmotic pressure and elevation of boiling point. The third one is pi is equal to del TF into dRT upon 1000 into KF. This is our depression and freezing point. Here KB and KF are molar constant of elevation in boiling point and KF is depression and freezing point. And D is the density of solution and R is universal constant. One more thing is there, when two solutions are separated by a semi-permeable membrane, the solvent will flow from the solution of lower osmotic pressure. Suppose the solution 1 has lower osmotic pressure and this has higher osmotic pressure, then the solvent will flow from the solution of lower osmotic pressure to the solution of higher osmotic pressure. So the solvent will move till the osmotic pressure of both this solution gets equal to one another. That is pi 1 is equal to pi 2. Here it is pi 1 and pi 2. So here solution 1 is having lower osmotic pressure and the solution 2 is having higher osmotic pressure. So the solvent will move from lower osmotic pressure to the higher osmotic pressure till both the osmotic pressure gets equalized. Now types of solutions according to osmotic pressure. On the first solution is isotonic solution. Isotonic solutions are those solutions which are having same osmotic pressure. These solutions are called isotonic solution. Second is hypotonic solution. If a solution 1 is having a low osmotic pressure and if the solution 2 is having high osmotic pressure, then this solution will be hypotonic solution. Third one is hypertonic solution. The same condition here, the solution 2 will be hypertonic solution. As it is having higher osmotic pressure. For isotonic or isoosmotic solutions, we can write the formulas. For isotonic or isoosmotic, isoosmotic is what the solutions having same osmotic pressure. Isoosmotic solutions, pi 1 will be equals to pi 2 or concentration will be equals to C1 or C2, or we can write N1 upon V1 will be equals to N2 upon V2, or we can write W1 M1 V1 will be equals to W2 M2 V2. This equation is only for those solutes which neither possess the tendency to get associated or dissociated. Only for those solutions which are not possessing associative dissociative properties. The next term is what is associative and dissociative properties. For that we have to study colligative properties of electrolytes. Colligative properties of electrolytes. These colligative properties depend on the total number of depend on the total number of molecules or particles present in that solution. As we know that in electrolytes get ionized in the solutions and will give more number of particles and give one particle per formula unit. In the solution. So the colligative properties of an electrolyte is always greater than that of a non-electrolyte. So the colligative properties for an electrolyte and for non-electrolyte it will be greater in electrolytes of the same concentration. If you are taking the same concentration of electrolytes and non-electrolytes, then the colligative properties of electrolytes will be more than non-electrolytes. The factors affecting colligative properties. Colligative properties colligative properties is directly proportional to the number of particles. If number of particles are more, then the colligative properties will be more. Number of particles or number of molecules in case of non-electrolytes, and number of ions in case of electrolytes. It is directly proportional to the number of moles of solute it is directly proportional to the mole fraction of solute. If total number of particles, number of molecules, ions, moles of solute or mole fraction of solutes are more, then the colligative properties will be more. The second is for different solutes, if we are taking different types of solutes, solute 1 and solute 2 of same molar concentration. Concentration is kept constant. Then the magnitude of colligative property is more for that solution which gives more number of particles or on ionization. Else are more, then number of colligative properties will be more. If we are taking different solutions, solution 1 and solution 2 of same concentration, of different concentration, then the colligative properties is more for that solution, which gives more number of particles on ionization. If it is solution 1 is giving more particles, then its colligative properties will be more. If we are taking different molecular concentration of the same solution, the colligative properties will be more for concentrated solution. For more concentrated solution. For solutions of different solutes but of same strength, percentage, then the colligative properties will be more for the solute with least molecular mass, least molecular weight. So these were the factors affecting colligative properties. Now, what is abnormal molecular mass? Molecular mass can be calculated by measuring any of colligative properties. Molecular mass can be measured by any of colligative properties, but it shows abnormalities due to association of solute molecules or dissociation of solute molecules. Now, what is association? When solutes in this is our solution, or we can say solvent, and here it is our solute. When solutes in solution associates means they get together, or it will go together like this, so this is association. In that case, it decreases the number of molecules. It causes the decrease in number of molecules, number of molecular particles in the solution, and results in the decrease of colligative properties. Value of value of colligative properties. As we know that colligative properties is directly proportional to the number of particles, or we can write colligative properties, the magnitude of colligative properties is inversely proportional to the molecular mass of solute. You can take one example as the benzoic acid. It gets dimerized in the benzene solution. So its molecular formula will be as dimer C6H5COH twice. So if it is in dimer state, then it will cause the lower osmotic pressure. So by associating of benzoic acid molecules, the osmotic pressure is get lowered. Now the next is dissociation. When a molecule dissociates in to give two or more particles, so it will exhibit the higher value of colligative properties. And the molecular mass will get lowered. The molecular mass of such substance will be less. It will be less than their normal value. Their normal value. If one molecule is dissociating in two or more, then its colligative properties will be more, and the molecular mass calculated from these colligative properties will be less as compared to their normal values. Now want Hoff factors. We have studied the about want Hoff factor. Now we'll study that what is want Hoff factor. It is denoted by I. I is introduced to express the extent of association or dissociation of solute and solution. Want Hoff factor I is the ratio of normal molecular mass upon observed molecular mass. In association, the normal molecular mass is less than observed. So for association, I will be less than 1, or in dissociation, for dissociation the observed mass is less than normal, so I will be greater than 1. If number of I is equals to 1, then there will be no association and no dissociation. So the observed molecular mass will be equals to the normal molecular mass. As we know that colligative properties is inversely proportional to the molecular mass, then I will be equals to observed values of colligative properties divided by calculated values of colligative properties. Assuming that no association and dissociation, or dissociation. So I will be equals to number of particles after association or dissociation, or upon number of particles before association or dissociation. So we can calculate the Van Hoff factor from these formulas. Now introducing of Van Hoff factor for colligative properties. For relative lowering of vapor pressure, after introducing I, it will be equals to P naught A minus P upon P naught A will be equals to IXB. And for elevation of boiling point, del TB will be equals to IKBM, and for depression and freezing point, it will be equals to del TF I is equal to IKFM, and for osmotic pressure the pi will be equals to INRT as we have studied earlier, or ICRT. These are the formulas of colligative properties after introducing the Van Hoff factor. From the value of I, we can calculate the degree of dissociation or association also. Degree of association and dissociation. Degree of association and dissociation is the fraction of total molecules which dissociates into simpler molecules or ions is degree of dissociation. So the alpha will be equals to I minus 1 upon m minus 1. This is the degree of dissociation, and m is the number of particles in solution, and degree of association is the fraction of total number of molecules which combines together or which associates together to form bigger molecule. So the alpha association will be equals to I minus 1 upon 1 by m minus 1. This is the degree of association, and m is the number of particles in solutions. Now the next term is Nernst distribution law. A solute distributes itself between two immiscible solvents in such a way that the ratio of concentration of solute in two solvents is constant at constant temperature. Provided that the solute does not undergo any dissociation or association. In any of solvent. So, according to Nernst distribution law, a solute distributes itself between two immiscible solvents in such a way that the ratio of concentration of solute in two solvents is constant at constant temperature, and it proves that the solute does not undergo any dissociation or association in any of solvents. So the C1 upon C2, the concentration of solute is directly equals to K. This K is the distribution coefficient or partition coefficient. This is the Nernst law, distribution law. The next is viscosity. The property of fluid of fluid, due to which it opposes the relative motion between the layers is called viscosity. It is also called as a fluid friction or internal friction. Or we can say the forces between the layers opposing the relative motion. Is called viscous force. If we are taking a layer AB is moving CD and MN, this is the distance X, this is the distance dx. This layer is moving from speed v, and this is v plus dv. Then we can write the friction force is directly proportional to the area. F is directly proportional to the A, and F is directly proportional to the velocity gradient. dv by dx, this is the velocity gradient. So we can write this equation together, these equations together. F is equal to F is directly proportional to A dv by dx, or we can write F is equal to minus eta A dv by dx. This is the formula to calculate the friction force. Here eta is the viscosity coefficient. Here the negative sign is showing that the force is acting in opposite direction of flow, and if A is taken 1, the area is taken per unit, and the velocity gradient dv by dx is also taken 1, then eta will become F. So in viscosity coefficient is the force acting per unit area between two layers moving with unit velocity gradient. Then eta will become F. So eta is the force acting per unit area between two layers moving with unit velocity gradient. If the viscosity of liquid is very much greater than gases, that is eta liquid is greater than eta gas. If we increase the pressure, uh, if pressure is increased, then viscosity of liquid is increased. It is except water. In case of water, if pressure is increased, then viscosity of water is decreased. These are for liquids, but gases are independent. As we know, there is no effect of pressure on the flow of gas, so the viscosity of gases will not change after changing the pressure. The friction of solid surface is independent of the area of the surface. And relative velocity between them, so there will be no effect. The viscosity of thick liquids is greater than thin liquids. Is greater than thin liquids, as we know that glycerin and honey are more viscous. Their flowing time is very greater as compared to the thin liquids. As thin liquids we can take water, so the viscosity of thick liquid is much more than thin liquids. The next is the viscosity of the cause of viscosity in a liquid is due to cohesive force. Viscosity of liquid is due to cohesive force, and in gases it is due to diffusion. So viscosity of gases is increased with increase in temperature. If we increase the temperature, then the viscosity of gases will increase. It is due to the diffusion of gases. The diffusion will also increase with the increase in temperature, so the viscosity of gases will also increase. And the viscosity of liquid decreases with the increase in temperature, or it is viscosity is inversely proportional to the temperature in liquids, because with increase in temperature the cohesive force between liquid molecules will cohesive force will in cohesive force between liquids molecule will decrease. It will decrease with the increase in temperature. So the viscosity will is inversely proportional to the temperature. The next term is surface tension. The next topic is surface tension. The property of a liquid due to which its free free surface tries to have minimum area, to have minimum surface area, and behaves as if it were in under tension, is called surface tension. If the property of a liquid due to which its free surface tries to have minimum surface area and behaves if it were under tension is called surface tension. We are taking one example. Here it is a liquid, and we are taking some molecules. There is different layers. And the one molecule is here and the other molecule is here. For this molecule, the total force of attraction is equal in all the direction. Suppose this is A molecule, this is B, C and D. For A molecule, the force of attraction in all direction is equal in all directions. So for the molecule A, the surface tension is 0. For the molecule B, for molecule A, the molecule will move freely inside the liquid. For molecule B, the force of attraction is also in equals, and it is just below the free surface. So the resultant force acting on it is also 0. For molecule C, it is below the surface, below the upper surface of the liquid. So number of force acting is downward. Here it is a very small amount of force of attraction is on upper side. So the total force of attraction is downwards. So for the C, the force of attraction is downwards. So it will experience a net downward force. And for molecule D, it is on the free surface of the liquid. So no molecules or on upper half. There is no molecule on upper half. So the no molecule on upper half. So maximum downward force is acting. So surface tension of a liquid is measured by the force acting per unit length on either side of an imaginary line drawn on the surface of the liquid. So we can write surface tension of a liquid is measured by the force acting per unit area, per unit length on either side of an imaginary line drawn on the surface of the liquid. Then T will be equals to F upon L. T depends on the nature of liquid, depends on nature of liquid and independent of the area of surface. Factors affecting surface tension is uh, surface tension is if we increase the temperature, then surface tension will get decrease. Surface tension is equals to 0 when it is having the boiling point on its boiling point. So we can write T is equal to T0 1 minus alpha T. So we can calculate the surface tension by this formula. Tt and T0 is the surface tension of liquid at T degree centigrade and 0 degree centigrade, and alpha is the temperature coefficient. Coefficient of surface tension. Example, machineries. Machineries get jammed during winters. Second factor is impurities. Impurities affect the surface tension if highly soluble impurities or substances like sodium chloride increases the surface tension of water. While as a sparingly soluble substances like phenol, it decreases the surface tension of water. So if we add highly soluble substances, then it will increase the surface tension of water, and if we put the sparingly soluble substances in water, then it will decrease the surface tension of water. So these were the factors affecting surface tension. Now application of surface tension. Uh, Oil and grease spots on clothes can be removed by water, and on applying soap, the surface tension is decreased and wetting power of soap is increased. So adhesive force of soap and oil is increased, and oil get mixed with soap and easily removed. The next application is surface tension of oil and paints is kept low, so that when painting or lubricating any machinery, it can spread easily. The third application of surface tension we can see when we pour some oil on a rough sea, it can be calmed. So these were the applications of surface tension.